is H2Core Systems from Germany. So, Mark, it's on you now.
Okay, so I think I was able to do screen share. You can see my screen?
Yes.
Perfect. I can't turn my camera on for some reason, but I guess it doesn't actually matter, huh? Okay, so morning, everybody. Thank you for your time and attention so far. I work for H2Core. H2Core is a German manufacturing integrator company specializing in the design, assembly, implementation of fully integrated hydrogen systems. We have built our sort of product set and our portfolio based around the Enapter AEM module. I'm also joined by my colleague Torsten Clausen, who's online, and we're both happy to answer any questions you may have. So I guess the fundamental challenge for many projects really is this Achilles heel of how we deal with storage. So in terms of hydrogen storage, there's a certain element of complexity and cost for the variety of storage options that can be used, particularly for many smaller scale systems. And more so where these systems are in areas like metro or residential or highly populated areas where you have space and, more importantly, security and safety type concerns. Less so if you're going to a remote place in the middle of the jungle, you have less people looking over your shoulder. But in terms of the storage element, I mean, in many cases, we find that the cost of storage can be as high as 40% of the total cost of the system. So while the Enapter AEM is nice in that it produces hydrogen at 35 bar pressure, and indeed that can be fine for many applications, we do provide low pressure 35 bar storage solutions in single vessels, which can be as large as 115 cubic meters, which could hold 325 kilograms of hydrogen. But being practical, a vessel of that size would be typically 40 meters long and weigh about 39,000 kilos. So the picture, I think, on the top left here, this represents a project we were looking at for a residential application in Europe. So basically, this user has lots of solar on the roof. Their solar downside, if you like, is only for 3.5 months of the year. So for 8.5 months of the year, they're able to produce hydrogen, but then they need to use that in 3.5 months. And based on the sort of the volume of hydrogen and the kilowatt hours that they require during the low PV season, it would require them to have a tank, which would be basically almost 4 times as long as the cabinet that the system would be in. Now, that's obviously a little bit impractical for a residential type application. We did suggest that the tank could be mounted upright, but the problem in that case would be that the vessel itself would be physically taller than the house. So the option of compression storage obviously has to be considered, and the solution in this case was a compressor which we were able to build into the cabinet. I'll explain more about how that compressor works, a buffer tank, and then using sort of high pressure vessels in racks to deliver the storage. So from a footprint space perspective, in this particular case, the compressor option overran, well over the option of just using low pressure vessels. So our approach to fixing the problem of storage really is sort of addressed in a number of ways. So we do provide solutions that will cater for Enapter's production process of 35 bar. We do provide storage solutions to suit that. But we've worked very closely with a number of, shall we say, compressor or pump manufacturers, in particular Maximator, Sauer, and High-T. And basically, they will provide us with the sort of the piston, the mechanical element technology, and we build the balance of plant around that. And in terms of the sort of compressor options, they could be electrically driven. In some cases, you may not want it to be electrically driven. They can be compressed air driven. And we're also working on solutions that use membrane approach, a bit like the electrolyzer itself, to transfer hydrogen from low pressure to high pressure. Our designs, wherever possible, we want them to be cabinet based. And our cabinet and our building block is basically a 19-inch rack type design in a 2-meter tall cabinet. And we offer the cabinet in two forms, either an outdoor cabinet or an indoor cabinet. And for countries such as, say, Northern Africa or India or a place like that, where the temperature can exceed 40 degrees, our outdoor cabinets would have an air cooling system to maintain that the ambient temperature. Where possible with cabinets, our approach is to sort of use the sort of concept of adding more cabinets rather than going into a container type space, because we find cabinets are a little bit more flexible in terms of allowing somebody to grow their system from, like doubling or tripling the capacity is easier to do by just adding more cabinets than it is by adding more containers. And in terms of the storage technologies that we want to support or we need to support, obviously they're pressurized vessels, and also more recently metal hydride. Metal hydride does solve some problems, all right, but there are issues to be considered with metal hydride, where if you make a mistake, your metal hydride can be severely compromised. And the storage solution of choice, low pressure compressor, high pressure, or whatever, is purely really based around the application use, whether it's residential or business, whether it's metro, a built up area, whether it's a remote area, whether the application is for refueling, manufacturing, load dumping for utilities, for example. And finally, and this is a topic in its own right, a lot of the design is also sort of directed by the local safety and regulations, which vary from country to country and even from region to region. So in overall, the sort of compressor options we have, they all seem to be named after DC comic characters, but the solution that we would provide for a small system, which could be, say, a signal cabinet with 2 electrolyzers, would be what we call our Aquaman. Physically, the Aquaman is the size of 2 EL 4.0s, so it fits nicely into our 19-inch cabinet. The compressor itself is actually contained in water. So the box itself has got a water tank, and the compressor sits inside that. And the advantage of that is we get no noise and no vibration. So it can quite easily, quite comfortably sit inside indoors. It doesn't have to be outdoors. So that is a solution that we see is very practical for, if you like, small single cabinet with 2 electrolyzer type solutions. The flow rate of Aquaman is about 1.2 cubic meters per hour. So it'll quite easily deal with 2 electrolyzers. And if you want more, you just add more Aquaman. The next model up is basically a scalable compressor that we've developed with Maximator. And it's basically got, it's a modular design type system. So the unit at the bottom is like a power and controller type system. And then each module allows you to step up your compression in stages. So the first module will allow me to go to 140 bar, second module up to 400 bar. And also we can grow that further to as high as 1,000 bar if necessary. Then for other sort of more larger scale type applications where the flow rate or the transfer rate needs to go from, let's say, 7 cubic meters up to as high as 48, we use the Mercury and Cirrus type compressor design. And these were a little bit more complex because they're physically larger. And but it's really sort of no upper limit, I guess, in terms of the type of compressor. Generally, it really depends on the country in question, but 300 bars seems to be the sweet spot in terms of cost and complexity. Going much higher than that, it's almost substantially more expensive and definitely more complex. So we've combined both the compressors and the electrolyzers into a container system really designed for refueling applications. And this is a product that we make that we have available to integrators and partners. Some of them use it as a refueling station, where we've incorporated a dispenser with this as well. And some of our partners also combine it with a fuel cell, so it becomes both a refueling station and, if you like, a potential backup power system as well. So in terms of the examples of this, we have deployed a number of these systems pretty much around the world. But in terms of the nicest example of the compressor type design and how clean this can look, I'm going to point to our recent deployment in the College of Weimar in Germany. I think it's got to be the nicest, cleanest installation that we've done. And also from receipt of order to delivery of the system, including the storage vessels, compressor, ELs, whatever, was approximately 5 weeks. So everything happened relatively fast. Yeah. So I guess the requirement that we were initially trying to address was a college that were implementing hydrogen as part of their syllabus. They didn't really have much to start with. They had an empty room, which we had to advise in terms of converting that to support the equipment itself. They wanted the compressor to be indoor, and they wanted to start basically small and then have the ability to double up or increase the capacity both of the hydrogen storage and of the compression side. And one of the reasons for that really was that the object of the system, the function of the equipment, was more as a sort of research platform for their students to measure things like efficiency and production rates and stuff like that. So in the solution we delivered basically would be our standard indoor cabinet. This is with liquid cooled electrolyzers, and they wanted liquid cooled because they were able to better measure the efficiency in terms of temperature loss and stuff like that. And we provided them with a half-size cabinet, which allowed them to go up to 300 bar with the option to upgrade that by adding another module, which basically claps down on top of the existing cabinet. This is, if you like, an overview of the room. I wish I had a picture of the room before we started, but you can see they have a treated floor. The blue lines here, these are the liquid, the cooling lines for the ELs. These silver pipes on the roof, that's the negative pressure ventilation system. So air is drawn out from the top, and it's put into the room on the floor level, and the room maintains a positive pressure all the time in case of hydrogen leaks or whatever. This is the piping that goes from the base cabinet to the storage, which is outside. Beautiful job of workmanship. The two thick lines at the top, pipelines at the top, are the compressor, the line into the compressor, and the return line from the compressor. And the return line from the hog compressor, in this case, also has the hydrogen purge included in that. That red object at the top here is a gas alarm. By law, it has to be a combination of a horn and a light. And this silver thing beside the cabinet here is actually a silencer system for the ventilation, to stop the ventilation system, bothering too many people. So if I go outside, for the initial storage, because they're operating at 300 bar initially, we're provided them with a 12-bottle rack rated to 400 bar. This is fairly standard product. It contains 12 bottles to standard 50-liter vessels. But as a general sort of observation, getting our hands on steel vessels these days is very problematic, partly due to the fluctuating price of steel. But we do stock these in many cases. The little tube with the yellow cap on it, that's a safety blow-off valve. The cabinet on the left here contains the air compressor, and the air compressor is designed to match the output of the ELs. So if the two electrolyzers produce 1 cubic meter per hour, the air compressor, we have a buffer tank, which is actually also inside this cabinet with the compressor. The buffer tank is one of these 50-liter vessels. And basically, when the EL fills the buffer tank to 30 bar, the air compressor comes on, opens, and starts transferring from the buffer tank to the high pressure vessel. When the buffer tank drops to 20 bar, the air compressor switches off. So the transfer rate is really designed around the hydrogen production rate, which is 1 cubic meter per hour. This is showing the lines on the, coming from each of the cabinets. They're on the floor. If anybody can tell me what that orange thing is in the picture within 15 seconds, we will give them a free EL 2.1. So I'm going to wait for 15 seconds. These obviously the blue line is the water line, the water coolant line coming out of the ELs, and that's basically it. It's all swage lock, all 1/4 inch piping, and minimum amount of bends and T pieces where possible. So if nobody has found the answer to that orange box, what that orange box is a small little pump. And the inside the system, inside our cabinet, we have designed a water trap system with a expansion vessel. And normally, if this system was outdoor, we would allow the water that's collected, the water that's collected in some of the lines, we would allow that just to dribble outside. Because it's inside a room, we use this small pump to transfer the sort of water that comes out of the purge lines, the condensation water. We use that to pump that out of the room. It's an option that we can provide. This is the plumbing, if you like. So coming from the room down here, from the hole in the wall, the hydrogen vent line has to go obviously past the building, so 1 meter high past the tallest part of the building, and that is probably our cleanest, nicest installation. So in conclusion, I mentioned before, we do a range of systems based around the AEM. These include like pure hydrogen production systems. In the picture here, I have 5 EL2s and a dryer in a single outdoor cabinet or indoor cabinet option. This can produce 5 kilograms per hour. We can cluster these. We can put this in a rack and put the racks inside containers if necessary. We can combine the hydrogen production with fuel cells. The fuel cells we use for the smaller systems are generally from Intelligent Energy, just simply because their form factor is perfect. However, we have to be fuel cell agnostic, and we've also worked with other fuel cell manufacturers such as Proton Motors, PowerCell, NedStack, just to name a few. The compressor solutions, as I mentioned, Aquaman is not pictured here, but Aquaman is available for the smaller type applications. For larger, we go for the Hydro Hulk, where we can go up to a variety of different bar pressures. We can also support larger systems. We can implement these in the form of, dispensing or refueling stations. And we've also done some, work around the multi-core product as well. So we basically serve partners, and these partners are the people who engage with the end customer, who determine with the customer what the solution is, and we basically manufacture the solution for our partners. Now, our partners can also include, and do include, Enapter partners. So if you're an Enapter partner and you have a project, we stock all the items. We can build your solution. You can put your name on the front. We understand the technology, and we can very quickly deliver the actual solution to your customer. As I mentioned, we have most of the equipment in stock. We have ELs in stock. We have cabinets in stock. Fuel cells may take a little bit longer because a lot of our fuel cell suppliers do have chip and component problems, but we also try to stock fuel cell modules. So we can pretty much build the system that you need in much faster time frame and do it relatively inexpensively, where the partner receives a system that's been built under quite strict compliance standards. It's already been commissioned, so you just have to turn it on and connect all the piping as necessary. Yeah. So finally, I think my 15 minutes is up. My contact details are here. Also, my colleague Torsten, who's our head of engineering. So please feel free to contact us if you have any inquiries or you have any projects you need help with. And I think that's me.
All right, Mark. Thanks a lot. That was pretty interesting. And thanks, Torsten, for your correction in the chat that it is 5 kilogram per day and not per hour.
Per hour.
So that's clarified already. Perfect. Thanks for that. Nevertheless, we got some questions. So are you ready for some?
Sure.
Okay. So the first one is on the H-port system that you showed. Is that ready for supply? And if you have any references that could be visited?
Sorry, you said that the what system? The
H-port.
H-port.
Yeah.
Yes, I would. Yes, it's already provided. It's the container system. So I think we probably need to bring you to a site to see one. Yeah.
Right. So in this case, they directly contact you to get an arrangement, right?
Yeah.
Okay.
Correct,
perfect.
Yeah.
Okay. And then there was somebody looking for the costs. So he mentioned that H2 storage is 40% of the total project cost, which seems to be a bit high. And he's asking if that is covering already transportation, groundworks, and so on, or if that is additional.
No, that's additional. And when I mention these figures, it does vary really depending on the requirements. So if I go back to that example of, if you like, large scale storage, because I need hydrogen for 3 months of the year, that's quite a big storage system. So it will vary. But I guess what I'm sort of saying in general is the combination of the price of steel, the vessel, and the compressor is quite a large piece of the cost. If you go for much larger systems like multi-core type size systems, the storage might drop from 40% down to about 25%. That price does not include the logistics of getting it anywhere. Yeah? That's just the material, the bill of material, or the component cost.
Okay, that makes it clear. Thanks for that. Another question, and partly you answered that already. So first part was the manufacturing of the fuel cell, which you mentioned intelligent energy due to the form factor that fits well into the cabinet. Yeah. But there's another question on the manufacture of the inverter to connect the fuel cell.
There's a variety that we can use. If it's a remote location and you need something, you need a Range Rover, I would probably say look at Victron. But to be honest, there many off-the-shelf units would be fine. Yeah.
Okay, good. Then a very special request: if H2Core can provide service to Asia Pacific countries. So if you deal in that market already, or if you want to.
Well, people ask me where I'm based, and I tell them I get my laundry done in Indonesia at the moment. So I don't live in Germany. I live in wherever the activity is happening. So I'm based pretty much full-time now in Southeast Asia. I regularly go to Philippines, Thailand, Vietnam, Indonesia, Malaysia.
So that sounds to be a clear yes.
Yeah, it's a very much a yes. Yeah.
Okay, cool. Then a longer question, let me just check what we have there. So in India, we have some places having ambient temperatures of about 48 degrees during summer. However, as per Enapter's AEM cluster project document on a certain page, the container shall always be maintained between 5 to 45 degrees Celsius for proper functioning of the system. In that case, we cannot use blowers for primary ventilation, as the ambient temperature outside is itself higher than 45 degrees. Now, if we intend to install AC systems in such situations, Then for a system of 40 electrolyzers, the heat load dissipated will be 200 watts times 40. Okay, I think that's ending up in a long calculation. So we are going to take that and get your feedback on that later on. Didn't expect that. Sorry.
Well, I'd like to compliment the person who asked the question. They obviously put a lot of thought into it.
Absolutely. And it will be answered, but not directly.
I think the answer best way to answer his question is we'll be able to show you something in India very shortly. So it's a similar problem in that the location in India, they experience temperatures almost as high as 50 degrees. So this is back to this quandary. Do I stick it in a container or do I put it in a cabinet? So the requirement in this application will be, if I remember rightly, 40 electrolyzers in 8 outdoor cabinets. Now, if I have a cabinet and all my electrolyzers are running, I will have airflow automatically being sucked in and going through the cabinet anyway. But to handle the anticipated higher temperatures of above 40, each cabinet has a bolt-on air conditioning system to get that temperature down. So the electrolyzers are okay, even up going past 40. The problem is their power supplies. Their power supplies can get quite upset if they're run hot. So we do have a solution for that. It's easier if the solution is implemented on a per cabinet basis than having, like, say, a 20-foot container, and you've got to try and manage the temperature inside a container using some form of heat management system. It becomes a little bit more complicated, in my opinion. Now.
Okay, thanks for offering that. And if you have use cases in the area, they should just reach out to you and get some arrangement on that done.
Yeah.
Okay, and then there is a last question from Akshay. Dimensions and weight of dryer and water tank, if you have that handy. Otherwise, we can answer that later as well.
I don't have the, off the top of my head, I couldn't tell you what the dimensions are. I can only tell you 19 inches wide.
Okay, and I see Philip is already providing some of the of our existing documentations, which includes dimensions as well. Perfect, thanks, Philip. Okay, no other questions for you, Mark. Thanks again for doing the presentation and for sharing your contact details. I have one last question left for Colin's presentation, if he is still around.
Yes, I'm still here.
Oh, great. So there is a person asking if your project, so your house, is existing. So I would answer that with a yes, just need your confirmation, and if it can be visited.
Yes, it exists. It's here. It's functioning, and we will take visitors. We do regularly. So if they'd like to contact me, we can make arrangements for them to visit.
Wonderful. Okay, cool. Then thanks again, Colin, George, Mark, for presenting your use cases, giving us all your insights. Thanks a lot.